Now we will see more details of this pipelining. One important detail I would like to discuss is about write back stage and decode stage. Just recall in write back stage what we are doing. Generally in the write back stage you will be writing the register, right, in the register file. Maybe your instruction is like this: add R1, R2, R3. Then here you will be writing R1, correct? That means you are adding R2 and R3 in the earlier stages. Then after that we will be storing the result in R1, correct? So at the same time, if you see, there is a decode stage. See the scenario, entire scenario, okay? So sometimes it is possible that write back stage and decode stage will happen in the same clock cycle. Sir, what happens then? What is the problem? They are two independent circuitry, right? Yeah, though it is, they are not actually exactly independent circuits. The reason write back stage is accessing register file, right? It is writing something into register, but in the decode stage we are reading the registers, correct? Example, let's say you have an instruction add R3, R1, R2. Then in the decode stage you will be reading R1, which is currently being written, right? That means someone is writing into R1 and you want to read it. If at a time both things happens, then unexpected results come, right? So that's why what I would like to say is there should be one systematic order. So always you can assume like this. So this is your clock cycle, a particular clock cycle, and remember one thing, generally we design our pipeline in such a way that every stage can be completed in one clock cycle. Okay, let's say this is a clock cycle and this is the duration. Now I can say that this is the first half, this is the second half. So your circuits generally will be designed such a way that, especially when this kind of things, then writing will be, what I can do is in the first half, then I design my circuit such a way that in the first half writing will be done, because that should be done first, right? Second, at the same time, to not to collide with this write back stage, in the later half, that means in the second half we will be reading. Okay, so if you do that, see, this picture clearly explains you. In the same clock cycle, in the first half I will be writing, and in the second half I will be reading, so that the data which is written by this write back stage will be taken. There will not be any problem. But sir, why don't you do like this, sir? How? In the decode stage, in the first half you read, in the write back stage, in the second half you write. If I do that, definitely you get the wrong answer, because if you consider these two instructions, add R1, R2, R3 and add R3, R1, R2, you tell me which one should occur first. Should we read the data first, or should we write the data first? Definitely we have to write, because this is the first instruction, right? So that's why I can say that if you do like this, then definitely you get wrong answer, because first you will be doing this one. That means the later instruction is reading R1, but it's supposed to read the updated value, but the updation is taking place in the next half cycle. That's why this is not a right way, right? So that's why by understanding the circuitry and requirements, I realized that the writing should be done first in the first cycle or first half of the cycle. In the reading can be done in second half. In that way generally people do. Remember that fact. Okay, now finally, whenever you have write back stage and decode stage, they can overlap, there is no problem. But to solve the problem, we have a problem, you understand. To avoid the problem of getting the wrong answers, writing should be done in the first half, reading should be done in the second half. In that way generally people plan. That is one architectural trick, I can say. Okay, now apart from that, still you need more details. Okay, I'm going to add one by one. So you understand the basic pipelining, I understood, but we have to learn so many details, like this is one detail you should learn to solve the gate problems clearly. Second thing what I am going to cover now, this forwarding, right? In the forwarding, sometimes what happens, we cannot do the forwarding, then what we do, then we introduce stall cycles. I am going to explain you how this stall cycles will be introduced. Okay, what is this stall cycle? Okay, we will see that. So now let me focus on operand forwarding again and this stalls. Now we'll see operand forwarding details. Already we have seen how to do operand forwarding, right? But now we will see in a more clear way. Okay. Example, let me take add R1, R2, R3 and add R3, R1, R2. Let me show what happens to these two instructions in the pipeline. So generally we write this kind of multi-cycle diagram. Okay. Now you see fetch, decode, execute, memory, write back stages, right? Sir, what is this one? Decode stage. Then what is this one? Decode stage. What is the difference? This is same decode stage as this one. These two are same, but we are writing two times. Okay. So these stages are explaining first instruction. These stages I am using to explain you instruction 2. But we have only one fetch stage, one decode stage, one execute, one memory, one write back. Okay. That you should understand. So this is a buffer between fetch and decode, that is fetch decode buffer. Similarly, decode execute buffer, execute memory buffer, memory write back buffer. So this fetch decode buffer, this fetch decode buffer are same, but they represent different content depends on the cycle. Example, at the first clock cycle, what is going to happen? Fetch will be happening. Okay, because of your control circuitry, then automatically instruction will be fetched because program counter will have that address of this instruction. That's why this will be fetched. Now I can say that at the end of the fetch, then instruction 1 as it is will be forwarded to this buffer. So I can say that the importance of this buffer is remembering instruction number 1, otherwise pushing instruction number 1 to decode stage. Now let us just focus on this first line, okay, so that we can understand entire story about instruction 1. After that, in the second clock cycle, what happens to this instruction 1? Then this instruction 1 already we have in this buffer, right? Then this decode stage at the second clock cycle is going to understand this instruction 1. That is what the meaning of decode. It will decode the instruction 1 and it will understand the binary patterns and it will realize that that is add instruction. Then appropriate control signals will be generated. So example, to do execute add instruction, what are the things we require? We know that we have to do so many things. They are all called all micro operations, right? To do all these micro operations, we require some set of control signals, C1, C7, C9, everything. So all that signals will be whatever the signals you want to enable. Example, program counter should be enabled or not. Did you remember? We had program counter enable bit. Then arithmetic logic unit. Adder should be enabled or not. Yes. For this instruction, adder should be enabled. Then what is the signal for that? C9. In that way, all that control signals will be sent through bits. Okay. Now you can understand like this. This buffer is going to have, because of this decode stage, we will send some control signals which are required to do the remaining calculations or remaining operations. So these control signals are very important. They are going to decide which machine should work. Okay, whether adder or subtractor or multiplier. Should we access the memory or not? Should we store the result back or not? Okay, everything will be decided by these control signals. Apart from that, the essential data. What is the data? In the instruction already we have R2 and R3. Then the content of R2, content of R3 will be taken from the register file. I can say that because of the decode stage, so there will be register file, right? So in the register file, R2 will be selected, R3 register will be selected, and the content, let us say 20,30, then 20,30 will be sent here. Though I am writing R2 and R3, that means the content R2 and R3 will be moved to this buffer. Now I can say that at the end of the second clock cycle, this buffer is going to have 20 and 30. Apart from that, R1 also, the identifier of R1. Example, let's say identifier of R1 is something, R1's address in the register file is 01. Otherwise, let us assume, actually it's a 5-bit number. Then what we do is we just assume that it's R1 address. Okay. The difference between R1, R2, R3 is nothing but the content of R2, R3 will be taken because of the decoding. Then address of R3 will be taken. That is already mentioned in the instruction. Sorry, address of R1. Okay, example, address of R1 is something XYZ. Okay, R1 means XYZ. Then XYZ will be passed. Sir, why XYZ is required? Because in the later stages, this executor is going to add that 20,30. It gives result 50. So I can say that let's blindly follow so that you can understand. So the execution stage is going to add 2030. That's why this buffer is going to supply the 2030. Then 2030 will be added. So that 50 will be passed to this buffer. Sir, why we are passing the result to the next stage? Because in the write back stage only we are writing the data into register 1. That's why. So 50 is really has to be passed. One more thing to be passed is XYZ. Okay, XYZ is nothing but address of R1. That means, sir, content of R2, content of R3 are going to be lost here. Yes, we don't want them, right? The purpose of content of R2, content of R3 is only for addition. In that way, you can clearly understand what is happening in this pipeline. In the memory stage, what happens, since this is add instruction, nothing will happen. It's like, just doing time pass. Okay, so we don't do anything. We spend that clock, we just spend the 10 clock and we do nothing. Okay, and we simply, in this clock cycle, I can say what we do is we simply move this 50 here and we move the address here, so that when in the 5th clock cycle, write back stage is going to add 50 in the register XYZ. So that register XYZ means 50. So this is a way add instruction will be executed. At the same time, see, parallelly second instruction also will be executed. Let us see second instruction independently. After that we'll club them. In the second instruction, actually what happens is R1, and forget about instruction number 1. First of all, instruction 2 will be fetched here. Then let me go a little bit quick because you understand this one, right? So that I2 will be decoded, so that content of R1, see, R1 and R2, content of R1 will be read, content of R2 will be read, right? So we are reading here from the register file here. Then address of R3, let us say ABC, then ABC will be forwarded. Okay, now R1, R2 means content of R1 and R2, ABC means address of R3 will be forwarded. So execution stage will take R1 and R2 as input. Such a way we have to design the circuit so that it will add them, because instruction is add, so appropriate. That's why the control signals which we are carrying. See, one more thing you remember, here we are carrying control signals, right? Some of the control signals will be discarded here. Why? Because they might be useful only for execution stage. Remaining control signals will be passed here, which are related to memory stage, write back stage. Now after that, some partial control signals will be used here for memory stage. Remaining control signals will be passed. In that way, control signals also will be pipelined or passed. Okay, so that these control signals are few control signals which are really important to do write back of instruction number 1 in that way. Okay, so now let us focus on I2. In the I2, finally we decoded the instruction and we forwarded some information. Now from now onwards, I ignore that control signals part, only I show you important details. So execution will add R1 plus R2, right? We get R1 plus R2 as one content, second one ABC will be forwarded. Then after that, memory stage will just simply push that R1 plus R2 here and ABC here, so that write back stage is going to write R1 plus R2 into register R3. So this is the way things are going to work. But there is a dependency actually, correct? You know that. See, you are modifying R1. Where are you modifying actually? In the write back stage, right? But you are using R1 here, right? In the execution stage. Here you are taking R1. This R1 comes from the decode stage, right? So the decoder brought R1 from the instruction. That means that is coming from instruction, right? That means decode stage is reading the register file, I can say. So this decode stage is taking the wrong data or old data. That's why we do operand forwarding. How to avoid that? You tell me, where is the fresh data of R1? Fresh data of R1 is available at write back stage. That means here we have, that R1's data is supposed to be 50, right? 50 is available here, that's it, after execution stage. That's why we have to connect this buffer to, otherwise, connect this result to something else. What we are going to do, that's why in our circuitry, so there will be a cable like this. It is nothing but data from execution stage that should be connected to where, either because you are going to use it for R1, right? We have to connect it to buffer like this. Okay, one comes from decode stage, another thing comes from this one. So that example here ABC, right? So what is R1 here? Sorry, R1 is nothing but here only, right? So in that way, this cable, that's why this is operand forwarding. Now if I take execution result 50 into R1, rather than this one depends on the circuit. I am not saying that always we have to forward. We have to forward when it is necessary, correct? Example, here it is necessary. That's why there will be a multiplexer. That multiplexer is going to decide whether to take this one or this one. Such a multiplexer we have to design. Without that, don't think that everything will be done automatically. Pipelining will have some control circuit again. So pipelining circuit, otherwise I can say we are doing forwarding, right? For forwarding there will be a circuit called forwarding circuit. So that forwarding circuit we have to realize, we have to design so that it should respond appropriately. I will tell you the functionality of that circuit. What that circuit should do is, it should somehow understand that there is a dependency between these two instructions. That means, first of all, this R1 should be written, then only that R1 should be read. You understand that, right? So appropriately, so that circuit should bypass the data, right? So there should be a cable like this, but it should not be used always. What we have to do is, based on these instructions, after observing the instructions, automatically the circuit should pass that value from here to here. Sir, how to design that circuit? Very simple. Actually, what happens, in the decode stage, we will be, example at third clock cycle. Okay. At third clock cycle, if this decoder is having instruction 2 and executor, I can say, is having instruction 1. So we'll do some modification so that we can design this circuit. What is that modification is? Let us have appropriate identifiers. Assume that, so we have identifier R1, identifier R2. Identifier means address. Okay. You have address of R1, address of R2, address of R3, which you are passing every time. Okay. That means when your instruction 1 is at execution stage, let's say this buffer is having all the identifiers. Now when this decoder is decoding the second instruction or whatever the instruction, that's identifiers are available in this buffer. Now what I want to tell you is, you design a circuit such a way that these identifiers can be taken. So what, sir? If I can take identifiers from this buffer and this buffer, what I am taking, example at third clock cycle, what I am taking, the identifiers of instruction 1, identifiers of instruction 2. Can I say that by that time, whenever you are decoding, by that time you have identifiers of instruction 1 and identifiers of instruction 2. Especially interesting identifiers, destination of the first instruction, that means destination of this buffer, okay, and sources of this buffer. Let us try. Let me take, the circuit is taking always, source identifier from the execution stage. Source identifier from the execution stage, if I take a third clock cycle, that will be definitely, sorry, destination identifier from the execution stage it takes, then it will be R1, and source identifier from the decoder stage, if they take source identifier, source R1, R2 or source, then you see, you will be having R1 and R1, R2. Then the circuit should be designed such a way that it should compare R1 versus R1 and R1 versus R2. Yes, it is possible. Just design a comparator. Comparator circuit can compare two binary patterns. So R1, R1 should be compared, R1, R2 should be compared. If let us, but sir, sir, already we know that they are matching, right? Why should we compare? That is already because right? Generally it will be like this: Ri, Rj, Rk. Okay. Ri is nothing but source identifier from the first instruction, destination identifier from the first instruction. Rj, Rk are source identifiers from the second. Then you compare like this. If Ri equal to Rj, that means the destination matches with first instruction's destination matches with one of the source. Otherwise you compare Ri comma Rk. After comparing such a comparator, if you design, then it will decide whether there is a hazard or not, correct? Yes, that's quite easy. Finally, I would like to say that yes, such circuit is possible. Try to understand in high level, then go to low level. Don't try to think in low level. First of all, when as a human being, can you say that there is a clash, right? Because you are reading from R1, you are writing into R1. So this identifier is already available here. Your decoder circuit, sorry, your that hardware circuit, which is generally related to this operand forwarding, will identify the hazard, then appropriate action it can take. To take the appropriate action, then we will be forwarding, otherwise we will be doing some other stuff, we will see. There are two things generally we do. If there is a hazard, then probably we can do operand forwarding. Sometimes operative forwarding might not work. Example, you have load instruction. When operating forwarding will not work? If data is not available. Simple. If data is available, always we can go for forwarding. Now, generally, whenever data is available, then we do operand forwarding. Then we generally do operating forwarding in two ways. Okay, how I forward the data is from the memory stage to execute stage, otherwise execute stage to execute stage. Okay, example here, I am moving the data from, because data is available here, right? Execute, you see, from the execute stage I will be moving to execute stage, right? So moving from execute to execute means my intention is the output of the execute stage is moved to input of the execute stage. Such a way we have to design a circuit. Understand? So this is the forwarding. Correct? But see, don't understand this like this. This E same, but only this difference is timeline. Correct? That means execute stage should be connected to execute stage. That's it. In the one line, if I show this is your execute stage, that is giving a output, right? That should be connected to again like this, and normal input. Generally, for execution stage, input comes from the decode stage. You know that. Apart from that, we should get one input from execute stage. Now, whenever the circuit detects hazard, then input should be taken from the execute stage rather than from the decode stage, because the input from the decode stage is wrong. Understand? So this is the typical circuit we use for operand forwarding. This is from execution stage to execution stage. One more thing is possible, which is memory stage to execute stage. What we do is we connect memory stage to output to execute stage. Actually, it is like this. But since we are taking two times, then it would be easy for us to show like this. The memory stage output to execute. It depends, like, at this moment it is not required. But generally we do sometimes. I'll show when we do memory to execute. Okay, generally we do that for load instruction followed by add instruction. Let us see that also. Okay, in this example I am going to teach you how to forward data from memory stage to execute stage. Sometimes it is required. You understand that slowly. Already of course I taught it because of the load instruction. We will see that thing. Then later we will see how to stall the pipeline. Sometimes we have to stall the pipeline. What is the reason for that and how to do the stalling? We will see these two. First of all, consider these three instructions: load, add. If you carefully observe, this third instruction is independent of these two. There is no data dependency. R4, R5, R6 are completely different from these registers. So now there is a dependency between load instruction and add instruction. Load is modifying R1, add is using R1. Now see what happens. If you see load instructions execution, first of all, load instruction, let us say I1. Okay, I1 will be fetched here. I1 will be decoded in the second clock cycle. I am only seeing the instruction 1's execution. Instruction 1 will be executed in the third stage. Instruction 1 will be, of course, in the instruction number 1 there is a memory access that will be done here, and after that write back of the instruction 1 will be done. Now what I want to tell you is, I don't show this time all the details. Okay, you know that, right? But I just show the essential detail. R1 is going to be updated at dash time in the write back stage, correct? So after write back stage only, the register file which is going to have R1 is getting modified. But if you see here in the second instruction, you are reading R1 so early, correct? Where are you reading it? You know that decoder stage, that means decoding stage is going to read that R1, correct? So in the decode stage we will be reading R1 and we will be taking the content of R1 and we will be pushing here. But unfortunately that will be old data, right? The new data is available after write back stage, unless you forward. Of course you can forward it, right? Sir, but we have the data available in the execution stage. No, you are wrong. In the execution stage for load instruction, already I told you, we only calculate effective address of the data, right, to be fetched. So here after execution stage what happens, 100 plus R2 will be calculated. Example, what is 100 absolute, immediate value 100. What is content of R2? 0. 100 plus R2 is 100, right? So 100 here, if this execution stage will just compute the sum of this 100 and content of R2. Then this memory stage is going to memory, and it is going to memory address 100. You see, main memory of 100 is actually X. We have to take that X and we have to store it in R1. Of course, you know that. So what I want to tell you is, after memory stage only we are going to get the data. Before that it is impossible, correct? This is the earliest thing, right? Now I can say that now we have data available 100, but that is not really stored. Where are we storing it? In write back. If you really want to forward, if you want to use data forwarding technique, okay, you can forward it like this, right? Data is available here. So we have to connect this memory stage to execution stage, right? So this execution stage, if you see, you want to add R1 and R2 to form R3. This is the earliest time. Actually here you want it, but you see the timeline. After 4th clock cycle data is available, but before 4th clock cycle you want it. How can we forward it? This forwarding is impossible. But if you can forward it, then we say that that is a forwarding from memory stage to execution stage. Understand? But that is not possible here because it's backward, right? It's not forward. You are not forwarding, you are backwarding. So for that you have to go back, in the timeline, backside. It is impossible, right? Can we travel backside on the time? No, that's fine. It is not possible. Then what to do? The only solution here is stalling the pipeline. That's why we stall the pipeline. So what is the meaning of stalling the pipeline and how we do it? So that is very important to understand the pipeline clearly. But in the GATE exam, without knowing these details also, you can solve some GATE questions. But to solve some tough problems, you should have complete clarity about what is happening inside. Without that, by remembering in the high level, by ignoring the important details, you can't solve difficult problems. That's why you should learn what is the meaning of stalling. Stalling is nothing but stopping this instruction. My dear, instruction 2, please stop. Don't get executed. But how to do that in the circuitry, I will tell you. I will explain that with one by one, like at the first clock cycle we will be fetching and we don't know anything about all this future, right? We do as it is. In the second line, in the second clock cycle, instruction 1 will be decoded. By that time also you don't understand that there is a hazard, and instruction fetch is going to fetch the second instruction. See, I number them properly. Now don't see the future, just you are at second clock cycle. Being at second clock cycle, what can we understand? We can understand that instruction 1 is getting decoded and instruction 2 is fetched. But by that time we can't say anything because still instruction 2 is not at all processed, right? That's why we have to go to third clock cycle. Assume that now we are at third clock cycle. At third clock cycle we have a knowledge of instruction 1 and instruction 2. We can design a circuit such a way that that circuit is going to take the identifiers from load instruction and proper identifier from the add instruction. I don't want to show that. Of course, that proper identifiers are, we should take a destination from the first instruction and that is available by that time, and source identifiers from add instruction, that means second instruction. Okay, R1, R1, R2. Since this R1 destination of the first instruction matches with source, then and we understand because already we decoded this load instruction, then we can form a circuit such a way that will understand that there is a need of stall. Without stall can we do it? No, because we are executing here, we want here, but data is available here. I can say data is available here, but you want here. It is impossible, right? We have to stop the pipeline for 1 unit of time especially, right? So if you can move this all computation, that would be fine. How to do that I will tell you. Generally what happens is, you will be having a circuit, extra circuit. That extra circuit's functionality I am telling you, that should do like this. Just be at the third cycle. Okay, we are at third clock cycle. We did not see the future so far. We don't know what happens in the fourth and fifth clock cycles. In the third clock cycle, what we do, we know. So the decoder is decoding this instruction, right? And it will understand that there is a hazard, and that hazard cannot be solved by forwarding. We can't do forwarding here, right? So what we will be doing is, we will be stalling this pipeline. The stalling means, what we do is, we simply send. So while decoding, what we do actually in this third clock cycle, while decoding, we understand that that is add instruction, and appropriate signals should be forwarded to execute cycle. In the next clock cycle, if there is no hazard, addition should be done. To do addition, generally what should happen? All the appropriate control signals should be forwarded. Already I explained you, right? This buffer at the fourth clock cycle, to get execution of this instruction 2, we have to send the proper signals. But I don't want to do that, because that will be mistake. That's why what we do is, example, in the execution stage there will be adder, right? That means we will be using adder, right? Assume that there is a control signal for adder. Let us call it as C1. What we do is, in general scenario, we have to enable the control signal at the fourth clock cycle, but don't do that. So disable it. That means send a signal 0 to C1. What I want to tell you is, whatever the control signals you are sending, right, send all zeros, not right ones. If you do that, what is going to happen in the fourth clock cycle, I will tell you. Let us come to fourth clock cycle. In the third clock cycle, what we did, because of the hazard is detected by your circuit, and it realized that we need to stall the pipeline for that. So this decode stage is sending all the zeros to the next level, so that I2 will be affected, right? What happens, we'll see. Come to fourth clock cycle. In the fourth clock cycle, because in the third clock cycle we did not touch the details of execution, the buffer of execution and memory. That's why instruction 1 will not be affected. We did not touch this part. We touched this part. That means we are manipulating the buffer between decoder and executor. Understand? Not between executor and memory. So that instruction 1 will not be affected, but instruction 2 will be affected. How instruction 2 will be affected? Simple. Execution will not be done. That means your data will be forwarded. Okay. So the data here will be forwarded. That means inputs will be given, everything. But we don't enable adder, and we don't send any signal. When you don't send any signal, generally what happens? Nothing will happen. Right. Then that is about instruction 2's execution in the execution stage. In one line, what we are doing is, we are not sending the proper signal, because this decoder understood that there is error, right? So immediately it will send all zero signals to all the control circuitry. From now onwards, every time. So this instruction 2 signal, focus on instruction 2. Rather than the correct signals, we are sending all zero signals, so that adder will not do anything. No one will do anything. No. In the next, I am only focusing on this second instruction. In the fifth clock cycle, what happens? These signals will be, all zeros will be forwarded here also, so that memory stage will keep quiet. Nothing will be done in the memory stage. Okay. Now if you continue that, in the sixth clock cycle, what happens? In the sixth clock cycle, write back won't get the right signals, so that in the register file nothing will be added. If really proper signals will be sent here. Now come back to third clock cycle. In the third clock cycle, if you had sent the proper signals, then proper execution would have been done, so that R1 and R2 would have been added, and the result will be forwarded to memory stage, and then the result will be forwarded to write back stage, so that R3 would have been properly updated. But that will not be done, because we are sending all dummy control signals. Understand? So that, example, let's say, I will give you an analogy here. Raju is your friend. He is just your, not your friend, he is your employee. What he has to do is, he has to purchase, there are 5 stages actually. Okay. He is working on 5 stages. How he is working on 5 stages? In the first stage, he will be taking your instruction. I mean, whatever. Let's say there are 5 stages. In the third stage, he should go to hotel. Let's say, because you said it. In the fourth stage, he should go to some movie. And in the fifth stage, he should do some extra work. What is that is? Maybe he should go to hotel, movie. Let's say he should go to some shopping. These are the 3 things you said to him. Okay. That is what the meaning of his instruction. But in the third clock cycle, what you realized is, so this employee should not do going to hotel, going to movie, going to shopping. Everything is correct. This should be done, this should be done. But in the third clock cycle, what you realized is actually he should go to hotel, and after that movie, after that shopping. But this time you want to stop him. What you do is you don't give money. Actually, you just tell him that I will be forwarding the money so that you can go to movie and hotel and shopping. That money is going to drive him. He will go to hotel, he will go to movie, he will go to shopping perfectly, and he can purchase everything and he can watch movie only if you send the data and if you send the money. Then what you do is don't send him. That means in the decode stage, this is the money required to do execution and memory stage and write back for the instruction 2. What you do is you send all the dummy signals, zeros, so that no execution will be done, no memory will be done for instruction 2, no write back will be done. Okay, now rather than seeing everything every time, let's focus on fourth clock cycle. In the fourth clock cycle, what we will be doing is we are simply sending dummy signals so that execution stage will not do anything, it will keep quiet. That is called bubble actually. Okay, so it will behave like a bubble, that means nothing. Next, so focus on fourth clock cycle, but focus on third clock cycle also. In the third clock cycle, what happened? Instruction 1 is properly executed, decoder is properly decoded the second instruction, and third instruction, you see, I3 is properly fetched, because I3 doesn't know that it should not be fetched, correct? That means instruction fetch stage doesn't know that it should not fetch, because in the normal routine, what should happen? In the third clock cycle, I1 should be executed, I2 should be decoded, I3 should be fetched. That is what happens. But later, after third clock cycle, second decoder stage realized that something, there is a mistake. Then immediately this decoder stage sends all the dummy signals. Okay, and what should be the right thing? This decoder stage should send the proper signals which are related to I2, correct? Now that's fine. Now I2 signals are all zeros, remember it, all zeros. Because of that, in the fourth clock cycle, now you see here, these signals are not disturbed, right? Only we modified these signals. There is a difference. Sir, what is the difference between these signals and these signals? These signals are related to, they are coming from decode stage of I2. These are all coming from execution stage of I1. These are all I1 signals. I1 signals are properly working. We did not damage them. We damaged only I2 signals. That is very important point you should understand, so that you can understand everything. Now we'll go to fourth clock cycle. In the fourth clock cycle, what happens? Because you did not disturb these signals, then this execution will be executed. That means memory stage of the load instruction will be done and 100 will come. Okay. Now, so here what happens is just bubble will take place. That means execution will not be done. Then sir, what are we going to do here? If you don't do anything for this fetch stage, that means actually what should happen is this instruction 3 should be decoded, but I don't want that. Why? Instruction 2 is not executed, then why you want to decode I3, correct? So here you should cleverly plan such a way that here also in the fourth clock cycle I2 should be decoded. For that, what we have to do, we should not consider this buffer. Again, what is this buffer is containing now? At third clock cycle, after third clock cycle, this buffer is containing I3, but I don't want that. I want what? Again I2. That's why this is one modification you should understand. What we do is we ignore this data, we take again I2 data and we decode I2. Such a way we have to design a circuit, okay, extra circuit. So if you do that, then that would be good. Now let us summarize. At the fourth clock cycle, what is happening? Instruction 1 is properly getting executed. Instruction 2 got dummy signals. That's why I2 is supposed to be executed, but it is not getting executed. It is stalled. Now I3 should be decoded. It's supposed to be, I3 should be decoded here, but we are decoding again I2. Now let us do that. Now come to fifth clock cycle. When we come to fifth clock cycle, normally, so this proper control signals comes here, proper control signals come here, so that I1 will be completing its write back stage. But here one thing, in the fifth clock cycle, the signals, this memory which it is going to get are nothing but the dummy signals again, which are just forwarded from the previous stage. so that again I2 will be doing nothing. So I2 is stalled. This is called stalling. Okay, stall is nothing but not doing anything. So finally I2 is not doing its execution stage. In the next clock cycle I2 is not doing its memory stage. Okay, now let us continue. What is going to happen here, so I2 is decoded, right? Now this time you continue normally, like don't disturb anything, so that I2 will be properly executed. In this fifth clock cycle I2 will be executed. This time don't send dummy signals. If you send dummy signals again, I2 will not do anything again, right? Now if you focus on the fifth clock cycle, let us revise. I1 is getting right back. I1 is getting right back. I2 is getting memory execution but dummy, nothing, really proper control signals will not be generated, so that we don't go to memory, we skip that memory, right? So but again I2 will be executed. Now we are executing I2 two times, one is dummy, second one real, so that here finally I2 is executed. See, actually I3 is fetched, but in the decode stage we decoded I2, so that next time when you move it properly, then I2 will be executed. Now focus on the last clock cycle, sixth clock cycle. In the sixth clock cycle, I1 is already write back is done, nothing will be done for I1. I1 is done, I1 says bye bye. I2 comes to write back, but again it's a bubble because the dummy data is propagating. So we are propagating the dummy data, so that write back stage also will be dummy. The right, actually if it is really right thing, then R3 should be modified. For that the appropriate control signals should be sent, but we are not sending, so that this is also dummy. That means finally because of these three stages are wasted, got wasted. They are not doing actual work. They are pretending like they are doing something, but they are not doing. Really there is no hazard. They're supposed to do execution of I2, they're supposed to do execution of memory of I2, they're supposed to write back of I2, but they are not doing anything. So now let's see the last one. What is happening here, memory stage is working properly, but it is working for I2, so that I2's memory will be done here. Then after that in the next clock cycle I2's write back will be done. Now what I want to tell you is it right? Is it correct one? Forget about I3. I3 will be later fetched again everything. So at this moment what I want to say is, really if you do like this, is it correct thing? Are you getting the right data? See here, focus on this I2 of execution. I2's execution when you are doing, finally this E is getting the wrong data, you see. Why? E is getting the data from decode stage, correct? But by that time R1 is not right one. When is R1 is right? After write back stage only, right? So this write back stage is updating R1. So if you see in the fifth clock cycle data is correct, but you are getting the data from the second clock cycle, fourth clock cycle, right? That is where your instruction is decoded, right? So that's why what I want to say is, here you have to do the forwarding. Of course I have shown here, let me show again. So finally what I want to tell you is, the data of R1 is available here and here, but this is the earliest point. It would be good to take from here. So from the memory stage directly you forward it to, you see, execution stage, right? Like this. That means here to this connection. So R1's old data here like this, and this is the new data, right? So which we are forwarding from memory, correct? So I can say that finally what you did here is the forwarding of data from memory stage to execution stage. That is one more way of forwarding the data, memory to execution. That means input of execution stage is taking the output of memory stage, right? Yes, it is possible at this moment, but before that we did a stall, right? There are two things here. One is stalling, second one forwarding the data from memory to execution. These two things we did here. So this is about stalling and forwarding the data from memory to execution stage. Now we will see how to stall a pipeline for 2 clock cycles. Okay. Now we'll see how to introduce 2 stall cycles. Okay. How to see the 2 stall cycles in the picture. I will explain that, don't worry. Example, when you get that situation is, there is no forwarding circuit and load is updating the R1 value. Add wants to use that R1 in the execution stage. Okay. If there is no forwarding circuit, then what happens, you see, fetch, decode, execute, memory, write back. This is about load. Now load is giving us data here, right? So here we have to do at least execution. If you do execution here, that would be fine. We don't get any problem. Sorry, but to get execution here, data is coming from decode stage, right? We can't execute here. We have to decode here. Try to understand. If second instruction, if you decode here, then is there any clash? No. Already I explained that, correct? This write back stage is writing the data in the first half cycle. Decode is reading the registers in the second half. So by that time already data is written, there is no problem. For that we have to fetch here. But unfortunately this kind of postponing is not possible in pipelining, because how do you know that we have to fetch this kind of instructions here? Are we, are we so intelligent so that we can predict that the next instruction will have dependency? No, right? That means we can't fetch here. We have to normally fetch the instruction here itself, but later we have to detect it. So that's why how this instruction will be fetched and how we will understand everything, we will see. Let me show with one example. Okay, so pictorially this will be the right idea to understand things. Let's take 5 stages. Okay, with this I explain you what is the meaning of introducing 2 stall cycles, how they will be implemented. This is fetch stage, okay, this is decode, this is execution stage, this is memory stage, write back stage. These are the fixed circuitry. Now only thing is varying is the instructions which are to be executed, correct? So sometimes first instruction will be fetched, after that the instruction will be decoded in that way, right? Let us understand the details with the clock cycles. In the early morning, at the first clock cycle, what is going to happen is I1 will be fetched, correct? So there will not be any problem for you. Let us take this example and let me show the stall cycles. Okay, now in the second clock cycle, what happens? Everything will be good. I1 will come to decode stage, I2 will come to fetch. Now, so we are decoding. Example here at the second clock cycle, you are decoding I1. By that time, you don't know about I2, so you don't know that whether there is a dependency or not. We can't predict anything. That's why we do normal. As normal. At the third clock cycle, they will be moved. Right? I1 with all its control signals and all its essential information, it will come to third stage. Right? It will bring all the essential details. So that means it vacates this position, decoding position, so that I2 will be moved here. So new instruction will be fetched. This is the way generally pipelining works. Now you see at the third clock cycle, decoder is decoding I2, executor is executing I1, fetch circuit is fetching the I3, correct? Now after end of the third clock cycle, what is going to happen is there is a circuit. Assume that we have some extra circuit. That circuit will detect that there is a dependency between these two instructions. Already I told you such circuit we can design which will read this destination, which will read that sources, and there will be a circuit. They will take the input R1 and this R2 and this R1. That means first instructions destination, second instructions source identifiers, and the circuit can detect that there is a dependency, and it will understand that the dependency is very big dependency because of load instruction. Such a way we have to plan the circuit, because by reading this, because already we know that the previous instruction is load, right, and the next instruction is add, and the dependency is 2 stalls. That means because of this dependency, to get the right answer, we have to, this second instruction should wait for 2 stalls. That means 2 clock cycles, correct? So how that thing will happen, I will tell you, because we are in the full flow, right? So for that, what we do is the circuit will detect the dependency and it will create 2 stall cycles. Creating 2 stall cycles happens like this. How you see? At the fourth clock cycle, nothing will happen to memory. That means I1 is having its own signals, they will not be disturbed. Okay, we don't disturb them. It is carrying its own signals, because of that it is doing its memory operation perfectly. Now this I2 is bringing its signals to this one. If I2 brings its proper signals with it to buffers, understanding, if I2 brings all its essential details to execution stage, I2 also gets executed, but that should not happen. We have to stop it. That is what stalling. What we do, I2's control signals we disable. So because example at the third clock cycle, what we do is we realize that there is a dependency. Already at third clock cycle we realized, right? So at the third clock cycle, we just at the fourth clock cycle we send only all the dummy signals. Remember, not the right signals. Okay, dummy signals. That is one important thing you should remember. So now I2 comes with all the dummy signals. Let me put a bubble like this. Whenever I circle like this, that means I2 is bringing all the dummy signals, so that there is no effect of execution of it, there is no effect of doing memory, there is no effect of doing write back. Example, simply I will tell you, there is an adder circuit. Okay, now I2 actually should add the things, right? To add the things, this adder should be enabled. Already I told you. Correct. What we do is, we don't send the proper control signal with I2. So I2 is not getting the proper signal, so that it will be, I will give one analogy. Like, I2 treat like a person. This person wants to open this execution. That means he wants to open adder. He wants to ask adder, my dear adder, please, I am giving you registers, please add them. But this adder will not respond. It asks to show me the appropriate password, that is control signal. But what we do is, at the third clock cycle we realize that there is a danger, right? So that's why while sending I2, see, I2 came from here to here, right? I2 brought all the dummy signals. All its passwords are illegal. Okay, they are expired. So that I2 cannot do its work. So finally, how to understand this one is, because of all zero control signals, then I2 will not be executed, right? Now, but forwarding will take place. Now, I3 supposed to come here, but one more thing we should do. We should not decode I3, correct? Why? Because I2 is not performed up so far. That's why in this one what we do is, still we take the old instruction only. That is one thing extra you should understand. What are we doing? Rather than taking from I3, when there is a stall cycle, at that period we have to take again I2 only. Such a way we have to create a circuit. Yes, it is possible. That means again bypassing. Should I take the instruction from fetch stage or existing one? So in that way we can plan it again. The same instruction we can take. Already we have that instruction. We take it again and we decode it again. Try to understand. Now, sir, what about this fetch stage? So this fetch stage can fetch now new instruction. Let's say, think about it. Sir, should I fetch a new instruction? If you fetch new instruction, what is going to happen? You see, I1, dummy I2, real I2, I4. Then where is I3? You missed I3, right? Not to miss I3, what we have to do is, we should not increment program counter at some point of time. What is that point of time? I will show that. Now we'll come back again, okay? So that now you can understand the things clearly. What I'm going to do is, at the first clock cycle, let's say whatever the program counter, let me assume that program counter is 100, okay? Because of that, I1 comes to fetch stage. This is program counter. Now time is 1. Now when time is incremented, when at the second clock cycle, because program counter will be incremented whenever fetch is done, so I1 will go to decode stage. That means I1's fetching is done. At that time, did you remember any instruction is fetched in that fetch stage? We also increment program counter. This time again fetch operation is done. Then fetch is going to fetch at 104, which is nothing but I2. Perfect. Now after that, automatically at the third clock cycle, what is going to happen is, I1 will be moved here, I2 will be moved here, I3 will come here. Why? Because at third clock cycle again program counter will be incremented. Because program counter is incremented again, then it will fetch an instruction at 108, which is nothing but I3. In that way, now see, in the first clock cycle, hundreds instruction will be fetched, instruction at 100. At second clock cycle, instruction at 104. At the third clock cycle, instruction at 108. You remember it, okay? Now at fourth clock cycle, what we have to do is important. At fourth clock cycle, by that time you realize that already in the third clock cycle you realize that this instruction I2 has a problem. We have to stop it. To stop it, what we do in the fourth clock cycle, we send I1 as it is to memory, but we don't send I2 as it is to execution. What we send then? I2 with all the dummy signals. We don't send the original signals. You got my point? Such a way we should have a circuit. So there should be a circuit which will have set of dummy signals, all zeros, and original signals. Original signals are already coming from decode stage. So this time I2 is moved to execution stage, but not with its original signals, all dummy signals, so that I2 will not have any effect on any register or anything, on arithmetic or anything. So now the question, sir, who will come to decode stage? Obviously it can come from I3, but I don't want to get I3 because I2 is not done, right? That's why I will repeat I2 here. So for that again you will have extra circuit. That circuit should bring I2 here whenever there is a stall cycle. This is what implementation of stall cycle. How stall cycle is implemented? You should have a very big circuit that will do all this stuff. So that now you understood that I1 is moved properly, I2 is moved properly, correct, but with dummy signals. Now who is coming to decode stage? Again I2. That means previous I2 is there, right? Same instruction we have to bring. Okay, now that is already in the buffer, we bring it. Now actually it's supposed to be I3, but we did not do that. Now the question is, at 4th clock cycle who should come here? Generally remember one thing. So now initially program counter was 100, then 104, then 108. See, at the first clock cycle program counter 100, at second clock cycle program counter is 104, at third clock cycle program counter is 108, at the fourth clock cycle program counter will become 112. But you want to introduce stall cycle, right? Really, if you want to introduce one stall cycle, program counter should not be incremented. That's why what you have to do is, actually where program counter is getting incremented? At fetch stage, correct? So at that time the fetch stage should not increment program counter. We have to disable the signals of program counter. That's it. Now let me tell you again. 1 2 3. Let me quickly do that. First clock cycle I1 is here, second clock cycle I2 is here, I1 is here, sorry, I1 is here, I2 is here. At third clock cycle I1 is here, I2 is here, I3 is here, and you realize that there is a threat. You wanted to introduce two clock stall cycles. That's why what we do is, after end of the third clock cycle, immediately disable program counter, lock it. Just imagination, we disable program counter so that program counter will not be incremented. So that means at 4th clock cycle again program counter shows same 108. Because of that, what is going to happen, we'll see. Now let us focus on 4th clock cycle. At 4th clock cycle, obviously I1 happily with its original control signal will come to memory, so that it will do this memory operation. But unfortunately I2 is getting only dummy signals. That's why I2 will not have any effect, though I2 instruction is getting moved here, but dummy, there is no effect on that environment. Now what about this one? Here again we move I2 only, okay, but don't put dummy, bubble here, because here we are really decoding it again. We are not dummily decoding, we are really decoding. Now here fetch is normal, whatever program counter shows you fetch it. So program counter is showing 108, that means it should fetch again I3. Now you see I3 is fetched second time, I2 is moved 2 times, I1 is properly working. Now in the 5th clock cycle, up to now 4 clock cycles are done. In the 5th clock cycle, what do you want to do? Do you want to introduce one more stall? If you want to introduce one more stall, what you do is, you continue the same story. This I2 also, see, I will show the movement. Mr. I1, please come safely. Yes. No. Mr. I2, blindly you come here as usual, but your signals are all dummy. You can't do anything to anyone, right? There is no effect of you. Now this place is empty. Now this stage is coming here, right? Then this decoder have two options at 5th clock cycle. It can send original instruction with proper assets or proper signals, or dummy signals. What do you want? If you want another stall cycle, send I2 with again dummy signals, so that this instruction also will not have any effect. Okay, let us do that, because I want 2 clock cycles, right? 2 stall cycles, 2 stalls. So 2 stalls are introduced like this. We are at the 5th clock cycle, remember it. Okay, that's why I1 is here, I2 is here, one more I2 dummy is here. Now again decode I2 only. Such a way we plan. Whenever there is a stall cycle, this decoder should decode the previous instruction. Now this fetch should fetch previous instruction again, because program counter is again locked, right? So don't release it. Now at 5th clock cycle also, so that will be dummy. So finally what I want to tell you is, we did 1, 2, 3 perfectly as usual, normal, but 4, 5 we did some extra things so that stalls are happened. Okay, now 6th clock cycle you should be serious. Okay, now you do normal. Normal means don't unnecessarily disable anything, blindly execute the instructions. See what happens. So at 6th clock cycle he will fall down like this. That means I1 says yes, I got executed. Now at 6th clock cycle, now I2 will be moved. The dummy instruction I2 will do write back, but because no signals are there with it, no control signals. When there is no control signal, no effect on anything. So nothing will happen because of I2, right? Then this is empty now. At 6th clock cycle, this will come here. Again that is dummy, nothing will happen. Now who will come here? This I2 with proper signals. See, at 6th clock cycle, really I2 getting executed, you remember that point. Okay, so far up to 6th clock cycle, I2 is not executed. It's supposed to be executed at 4th clock cycle or something, but it did not happen. Now let's move I3. Since this time you want to be serious, then you seriously execute I3 as usual. When you move I3 here, then I4 will be fetched, because program counter will be incremented, because this time we did not disable program counter, so program counter will be incremented. So I4 will come at 6th clock cycle. I4, sorry, first this is wrong. Actually we should not enclose the I3. Everyone is serious. Serious I4, serious I3, serious I2, dummy I2, dummy I2, because of 2 stall cycles. This is at 6th clock cycle. So at 6th clock cycle, already I1 at 5th clock cycle, end of the 5th clock cycle itself, I1 got executed. Now at 6th clock cycle, already I1 is out of the pipeline. Now see, at the end of the 6th clock cycle, I2 will come out, right? I2 will come out. In that way it will be continued. Don't worry about the remaining story. So this is about the story. Understand? Now the same thing I will show in the boxes, because in the exam, how to solve these problems quickly, how to understand the stall cycles quickly, I will tell you. Because sir, then why did you teach us these difficult things? This is actually the reality. This is all our imagination to solve the problems quickly. Then we will be we are not understanding all the details. In this previous thing we understood all the technicalities, right? But here we are not understanding. But in the GATE exam it will be good to remember this also. That's why understand the difficult things, understand the real details, and understand how to solve the problems in the GATE exam, right? Now see, at 1st clock cycle instruction will be fetched. Okay, now this is one more way of understanding the same thing. How to understand 2 stall cycles is a question. Now it will be easy for you, because already you had enough foundation. Now see, 1st clock cycle, fetch 1, instruction number 1 will be fetched. 2nd clock cycle, instruction 1 will be decoded, instruction 2 will be fetched. Now at the clock cycle 3, execution 1, decode 2, fetch 3. This is the place where you realize that instruction 2 got problem. Then you thought of introducing 2 stall cycles. That means you means your circuitry. Okay, so such a way automatic circuit we have to design, which works based on the instructions. Now that's why, because of that 3rd clock cycle, 4th clock cycle will be modified. So it's not like this. This is general idea, right? F1 D1 E1 M1 W1, F2 means 2nd instruction, 3 means 3rd instruction. This is normal thing, but now we are not doing normally. At 4th clock cycle what we do is we send 2nd instruction with dummy signals. That's why there is no effect of execution. That is what I said. So 4th clock cycle you understood. But remember one thing, at 4th clock cycle, did you decode D3? You supposed to decode D3, but what we did, because of our circuitry, we decoded D2 only. Now everyone try to understand up to 4th clock cycle. Up to 4th clock cycle, if you see what happened is, first instruction is at memory, 2nd clock instruction is at execution, but dummy execution. 3rd instruction is not at all in the picture, because we cheated it and we are decoding the same instruction, which is 2nd instruction. That is what at fourth clock cycle. Okay. Now, but see, third is fetched. Third instruction is fetched, but we are not using it, right? That's fine. Fetched F3, but decoded D2. So instruction 3 is not at all moved to next stage. Now come to fifth clock cycle. In the fifth clock cycle, normally first instruction is executed. Because you know this instruction is carrying dummy signals, this memory also will become dummy. Now this one, what about this one? Since you want to introduce two stall cycles, this decoding also will be done so that second instruction again will be made dummy by adding dummy signals. If you add dummy signals, and one more thing, can I change this to E2? Because we are decoding instruction 2 and we are moving instruction 2 only, right? Now this is a correction, because at that time initially we thought it's normal, but it's not normal. So third instruction is fetched at third clock cycle, but second instruction is decoded. Here the same instruction which is decoded is forwarded to next, which is execution, but dummy. Already same thing, whatever I taught already, that I am showing. Now you see, second instruction is made 2 times dummy, here and here, right? Now at the sixth clock cycle, at end of the fifth clock cycle itself, instruction 1 is done. Instruction 2 is acting like it is getting executed. Instruction 2 here also acting like getting executed. So there are 2 instructions on the pipeline, I2 and I2, which are both are dummy. Now in the next clock cycle, what we are going to do is, this time we will be serious, correct? So that we will be really fetching F3 again, but we are seriously decoding D2 and we are seriously executing E2. Understand? So that means what? Here we will be fetching F3, here we will be decoding again D2, right? Because we are introducing 2 clock cycles. You can understand like this. In this row we will be decoding D2. See, in this row we will be decoding D2, in this row we will be decoding D2. This time we will be seriously decoding. That means we are using the result of this decoding. Now, so here D2, then again after decoding, execution, memory in the later timings, write back, right, W2. Now let us focus. I am not writing the remaining things, but I would like to say one thing. Since this E2 is, this instruction 2 is doing dummy execution, so that here also it will be dummy memory operation, dummy write back, because all the signals it is carrying is dummy signals. Similarly here, this will be dummy. So I can say that this decoding is unnecessary. That means it is not fruitful. That means not effective. This decoding also not effective, right? So but on this F3 unnecessarily, but we can't do anything. This is one of the implementation. So you are fetching F3 so many times, but we are not using. Okay. Now in the next level, we will be seriously fetching F3 to use it. Now it will be like this. Next time again we fetch it F3, then we decode D3, then this time it will be F3 D3, it will be E3, it will be M3, it will be W3, in that way. So things will be carried away. I did not show what is I3 here. Assume that I3 is one of the instruction. Okay. So this is the way stalls will be introduced, right? Now focus. It is normal F1 D1 E1 M1 W1, but here because of the stall cycle F2 D2, but dummy E2, dummy M2, dummy W2. Again fetch third instruction, because by that time I don't know that we are going to have this kind of problems. That's why we fetched normally, but we decoded old instruction and we dumbily executed E2, M2, W2 here in this row. Now here again F3 will be fetched, but D2 will be decoded, but this time seriously it is executed, right? Now at 6th clock cycle, if you see, this is dummy execution, here dummy memory, but here serious execution of E2, right? Serious decoding of T3. Understand? So this is a way stall cycles are introduced. Now one more thing, you don't really require to write all this stuff. From now onwards you remember. After this one, this is useless, however, right? This entire set is useless, right? But it happened. This entire operations are useless, but they are happened, right? They got happened. Sorry, this one. This entire thing is useless. This entire thing is useless. But This is useful, correct? So though you are fetching F3 but you executed I2. Can I say that? So from now onwards I write like this for shortcut F1 D1 E1 M1 dem1 W1. This is what the reality, but effectively if you see, this is real execution of I2, right, where it begins at fourth clock cycle. 1 2 3 4 5 6 7 8 9. From now onwards in the gate exam, whenever they say that there are two stall cycles, how to understand that is, see F1 D1 E1 M1 W1, second thing should start, second instruction should seriously start at fourth one. That means you can feel like this. That means if you write here F2 D2 E2 M2 W2, then that would be equivalent to this one, right? Now F3 at fifth, F3 D3 M3, sorry, E3 M3 W3. Now this is the way things will be executed. So here there is a emptiness, right? This indicates that there are two stall cycles. So this will be the final shortcut. But this is real implementation, right? So this is about stall cycles.